This is 1982 IMO problem number 3. Here is a view of this problem. We're given an infinite sequence with terms x sub n, and the general term. These are all positive real numbers such that x sub 0 is 1, so this guy is equal to 1, and they are a decreasing order, right? So this is a decreasing sequence, but notice that all the terms are greater than 0. The question is two parts. In the first part, we need to prove that for every such infinite sequence, we should be able to find an integer n greater than or equal to 1 such that an index that will make this partial sum, the partial sum greater than or equal to 3.999. Okay, let's focus on the first part, and I'll try to answer the second part. Let's consider the full sequence. So the full terms, like the sum of this sequence, the sum of the so we have x sub 0 square. Well, x sub 0 is really 1, right? So we know that. So let's just cut it short and let's just write it as 1 over x sub 1 plus x sub 1 square over x sub 2, and so on. X sub 2 square over x sub 3. But instead of stopping at this term, we keep going on, right? So x sub n square over x sub n plus 1, and so on. Now, one natural question is the sum of this sequence. Well, we don't know for sure if this sequence will converge or diverge, but I will still use the letter L. When I say L, I still so L, where L is L is an element from because it has to be greater than 0, right? So from 0 to infinity, but really including infinity, right? So I'm not avoiding union infinity, if you will. So then, so what is the trick then? So we have this infinite sequence. Of course, if I can show that L is, say, greater than or equal to at least 4, right? Do you agree, So show this. If I know that the infinite sum add up to something greater than or equal to 4, I can always interrupt the sum at some point where the partial sum is greater than or equal to 3.99, basically, right? I can squeeze it somewhere between 4 and 3.9, because the only way that well, these terms are always decreasing, so as they decrease, for instance, if L is finite, so each of these terms are approaching 0, right? So therefore, obviously, we should be able to find the distance, which is, and if it is divergent, that's obvious, right? So I don't have to worry about that case at all, because I mean, I go far enough and I will definitely always exceed this number. Okay, so once we establish that, now we know what our goal is. Our goal is to show that this L is greater or equal to 4. That solves the problem. The trick for that is actually very simple. It turns out that, okay, let me write that down. 1 over x1, I will factor out, so the rest of the expression, this infinite sum, I will factor out x1. It's actually pretty tricky. I mean, it's obvious. So it's x1 over x2 plus x2 square over this term, x1, x3, I guess, and so on. We should have x3 square over x1, x4, and you can keep going on forever. But what is the benefit of doing that? Well, the benefit is it's very nice. It turns out that it is possible to rewrite this expression as the following. I can make it look like this sequence again. How can it be? Well, look at that. So let's focus on the inside, right? So let me use a different color. So so this is just the first term is just so this is equal to the first term is I'm just gonna write it like this, and this gives me an idea, right? So so we have the 1, the x1. Hey, I can create a new sequence. I can call this as y1. And because I already know y1, so x2 over x1, I know that this is y1 square, so I will get a y1 square here, and I can imagine what y2 will be, right? So I need to make this one look like y2, right? And it's now a matter of simple computation to do you guys see what I'm doing here? Y3 and so on. So for instance, I want to make sure that this term here is actually mimicking this guy here, right? So, but I already know y1 is x2 over x1, so therefore this thing is x2 over x1 squared, all divided by y2, and I need that thing to be equal to that guy here, so it's just x1 squared over x2. So therefore from here we can get y2. Y2 is what? X2 times x2 square over x1 square divided by x1 square. Yes. Is that right? I hope it is, unless I messed up as usual. X2 cubed over x1 to the 4th power. That is not what I needed. Apparently I messed up again. Okay, so just give me a second. So we have 1 over x1. So this is just x2 over x1. Yeah, that's a y1, right? And then I have x2 square over x1 x3, right? So because it's this term here, x2 x1 x3. I did another silly mistake apparently, right? So, and I want this guy to look like this because it's the second guy. So it should look like really y1 square over y2, but so these two so this guy should resemble that. So I can replace the y1 square, because I already got it, x2 over x1 squared, all divided by y2, and that better be equal to this guy, x2 squared divided by that's the wrong one. X2 squared, sorry for that. X2 squared, this guy, not the previous guy, this guy. X1 x3, okay, sorry for that. Okay, x1 x3. Okay, now I should be good. So therefore y2 is just what? X2 squared over this one is x1 x3 here. X1 x3 times, obviously. So x1 times x3 times this guy, and then I divide by x2 squared. Yes. Okay, so the x2 squares cancel out. Hey, boom, the x1 and this square. This is just so this is just x3 over x1. Does that make sense? And once you get that, now it's obvious what the main idea is. So therefore the sequence that makes it work is y sub n equals x sub n plus 1 I don't have a square, yeah, divided by x sub 1. That's it. And let's investigate if this new sequence satisfies this property, and I hope it will, right? So let's start with y0. Y0 is just x1 over x1, which is 1. That works. So y1, right? So let's quickly calculate y1. Y1 is just x2 over x1, but x2 is less than or equal to x1, right? So therefore, this thing is definitely less than 1, but so therefore it is less than y0, right? So we have y0, then we have y1, which is less than y0. So let's go ahead and do that. So less than or equal to, let's say, and so on, right? So in a similar way, I can calculate y2. Let's do it one more time, maybe. Y2 is just x3 over x1, but notice that x3 is even smaller than y2, so therefore yes, that works, and so on. and that those are all greater than, strictly greater than 0. Wow! So why did we do that? Now we understand that, so let's rewrite this expression here. So L is equal to 1 over x1 plus x1 factoring out, and look at the inside. The inside is just a new sequence. Let's write it 1 over y1 plus y1 square over y2 plus y2 square over y3 and so on, right? But this is just the same thing as the x1 sequence, right? Because where y0, which is equal to 1, by the way, is greater than or equal to y1, y2, and so on, greater than or equal to 0. That's just a renaming of the whole thing, which we decided to call the whole thing as L. Now we can finish this problem, right? So we can factor, actually, do I want to solve a quadratic here? Probably not. That would be silly. Okay, yes, instead I will, okay, let's write it. Okay, let's first rewrite it carefully. x1 plus x1L. So this is a standard trick. We will just use AMGM here. So you have these two terms. This is the sum. So this sum is greater than or equal to the product, which is L, right? x1s cancel out. So, and then there's a 2 here, 2 square root L. And that's it. So this implies squaring now both sides, because L is positive, obviously. L square is greater than or equal to 4L, which implies, but because L is greater than, so it's L implies greater than 0. L is greater than or equal to 4, as we desired. That's it. So we have just found that the infinite sum is greater than or equal to 4. So therefore, I can always cut the sequence. Well, if it's divergent, obviously there's nothing to prove, it's obvious. If it's convergent, then each of these terms gets closer and closer to 0. So we should be able to find like one of the terms which is eventually less than 1 over 1000, right? So x1, so this guy will eventually get less than this number, and that does the trick. Okay, now for the second part, we need a construction here. Show that we can find a sequence such that for all n, this partial sum is strictly less than 4, regardless of where I cut the infinite sequence, right? So I need to be careful here. For this one, instead, so rather than showing that the sum is greater than or equal to 4, I need to find a sequence, a particular sequence, where the sum, the infinite sum, is exactly equal to 4. So therefore, anywhere I cut the sequence, of course, when I have any, okay, so yeah, that makes sense. Okay, so we have find, let's call this sequence the z sequence, z0 square over z1, plus z1 square over z2 plus z2 square over z3 and so on. So we want this infinite sum to be exactly equal to 4. So therefore, wherever I cut the sequence, the partial sum is always strictly less than 4. Now, because this is a constructive idea, and this reminds us of the best sequence that we know, that the best series that we know converges is geometric series, and you want convergence to 4. This gives us an idea of using geometric sum where the ratio is 1 over 2, right? So the geometric ratio between consecutive terms is 1 over 2, and indeed you can come up with the following sequence. Ultimately, z sub n is just equal to 1 over 2 to the power n, and indeed if you plug them in, or before I do, let me just calculate z0, z1 and so on. So z0 is just 2 to the 0, which is just 1. z1 is 1 over 2, obviously, right? So 1/2 basically. z2 is equal to 1 over 4 and so on. z3 is 1 over 8, and you can keep proceeding in that fashion. So therefore, our sequence becomes like this. Yeah, let's just substitute. We can substitute each of these into our sequence. We get that, z0 was just 1, right? So 1 over, so this implies, so we don't know that if it's 4 or not, right? So actually, let's do it like this. So we want to find something which is equal to 4, so question mark here. So that thing, the right hand side is definitely equal to 1 over z1, which is 1/2, plus a 1/2 square over z2, which is 1 over 4, and so on. And then the next one would be 1 over 4 square over 1 over 8. I can keep proceeding like this. So this guy is equal to 2, plus you have 1 over 4 here. This is a 1. You have 1 over, oops, sorry for that. We have 1 over 4 square, which is 1 over 16, divided by 1 over 8 is just 1/2. Yes, that just works, right? Let's test one more term. So 1 over 8 square divided by 1 over 16. 1 over 8 square is just 1 over 64, which is 1/4 of 1 over 16, obviously. Yes, we have it. We have it. And obviously you could have alternatively used summation sign, I guess, but this is nice already. So I can factor out, say, a 2. Yes, so that would be 1 plus 1/2 plus 1 over 4 plus 1 over 8 and so on. Oops. And that's just 2 times. This is just 1 plus 1 over 2 plus 1 over 2 square plus, so you have an infinite geometric series where the ratio is just 1/2. So this is just yeah, I think everybody knows what this is equal to. 1 over 1 minus 1/2, 2 times, and this is 1/2, so 1 over 1/2, which is just 4. Yes, so we have just found a special sequence, a sequence where the infinite sum here is exactly equal to 4. Therefore, anywhere we cut the sequence and get the series and get the partial sums, of course the partial sums will be strictly for all n, for wherever you cut, doesn't matter you cut it here or here or here, they will all be strict less than 0 because each term is greater than 0. And that solves that very interesting problem. Hope you enjoyed it and looking forward to see you guys in our next lecture.